presentation is entitled Comparison of Crack Propagation Rates in Selected AISI 304 grades, 3-point bending test, and is presented by Tereza Juhászová. Okay.
Good morning. Oh, okay. So my name is Tereza Juhászová, and today I'm going to present you my research on what you already heard. I'm first year PhD student at Faculty of Civil Engineering at Brno, and together with my research group, we are from Institute of Physics of Material of Academy of Science of Czech Republic. So, okay, sorry. So in the beginning, I'm going to talk a little bit about numerical modeling I did. Sorry, my numerical modeling I did in ANSYS Mechanical, then the actual fatigue testing we did. Then I'm going to talk about the fracture parameters we evaluated using numerical modeling and fatigue testing in combined. And then in the end, I'm going to talk about the Paris law evaluation that was the main focus of this part of the research. So, in general speaking, I'm going to talk about 3-point bending specimen with single edge on the bottom of the specimen. It's made of stainless steel, and the ratio of span of the supports to horizontal vertical dimension of the specimen is calculated to 3. So numerical modeling took place in ANSYS Mechanical, and 2D and 3D specimen were made, but today I'm going to only talk about the 3D specimen. So basically the 2D specimen is the same but without the thickness, so it was like a 1 millimeter thickness, like the plane condition. So this is my numerical model. It's from, as you could see, ANSYS Mechanical. We only made like a quarter of the specimen, and the rest was replaced with boundary conditions in the thickness or in the span way. The loading was simplified as linear, and also where the supports, as the rolled supports, were modeled as boundary condition. The crack were modeled on the bottom as area without boundary conditions. So the material parameters in the model were Young modulus of 190 gigapascal and Poisson's ratio of 0.3 that corresponds with the stainless steel. Crack was modeled, that's wrong. Crack was modeled as a relative crack length in ratio to vertical, I'm sorry, to vertical dimension of the specimen from 0.05 to 0.5. And stress intensity factor was calculated on a path that, I'm sorry, this is wrong. The path was supposed to begin in the crack tip, and it went vertically through the through the undamaged body of the specimen. So on this path, we took opening stress, and we evaluated the stress intensity factor at the tip of the crack using direct method. As you can see, this is the graphic evolution of the direct method. So you do the relationship of R, what is the the dimension like from the crack tip, and K1 to each point of this path, and then you do the linear curve to evaluate the stress intensity factor at the crack tip. So in the beginning, we needed to check if the model was right. So we did it as we compare it with Tereza's evaluation for S2W4. As you can see, like it was pretty precise, but we needed to as you can see, like in the beginning, there is a plastic zone, and we needed to do the stress intensity factor calculation without the influence of this stress plastic zone, so the data would be more precise. So then we continued. This is the actual specimen. This is the fatigue testing we did. And so it's 3-point bending of specimen with thickness of 10 millimeters and horizontal dimension of 30 millimeters. The R stress ratio we used was 0.1, and the maximal strength used was 25 kilonewtons. What we measured for each 100 circle was crack mouth opening displacement using this cage extensometer, and we have two productions that were Asian production and Europe production of specimen. So this is the example of experimental data we got from the measurement. So what we needed to do was to edit the model, because as you can see, these planes on the bottom have dimensions comparable to the specimen dimensions. So we needed to edit the model a little bit so we can actually calculate the crack mouth opening displacement and not the crack opening displacement, because they weren't the same. So for each crack length, we calculated from the model CMOD, and we adjusted it, so we found the closest value from the experimental data. Then we evaluated the relation between CMOD and K, as you can see, and I fitted it with the polynomial curve, and then relation between CMOD and the relative crack length. As you can see, it was with a logarithmical curve. And all of this leads to actual point of this research was to evaluate the Paris equation. I think everyone is familiar with it. So what we actually had was the number of dn. It was like 100, because we have the data for every 100 cycles, loading cycles. dA, what is relative crack length change, was measured using the relationship using FEM, and also decay was measured using final element method. And so we have all three of these, and we wanted to calculate the C and M, the constants of Paris equation, and that we did afterwards. Like we needed to plot dA to dn and delta K in logarithmical scale. And this is how it looked like in the end. So it's not exactly, it doesn't exactly look as a Paris, like as this graph, as you can see, but you can still use it, like you can calculate the threshold value, and we determined also the critical value as a change in a curve, like you can see at this point. So it was determined at 100 megapascal. Sorry, it was supposed to be meters on 1/2, on power of 1/2. So as you can see, there are not radical changes. Like the results are pretty similar. There are small changes in the threshold values, but practically the critical values are the same. And so in the end, we calculate to present the results a little bit better. We use the linear fitting for this region, and this is the result. So as you can see, like in the beginning, there are slight changes in the curves for European and Asian productions, but in the end, the results are almost the same. And so the main focus was to calculate the coefficient and so C and M, but the M is actually more important because it's the slope of the curve and it determines how fast the crack grows. So in the end, in the Asian production, the crack grows faster than in European production. And in comparison with construction steel, where these values for M are 2.5 and higher, these results are pretty good because we are at the bottom of this interval. And for stainless steel, it's a little bit lower, but we are still like in lower values. So we are like satisfied with these results. Okay, so what this will be used for in the future is like what we wanted to do is to determine the influence of stress ratio on crack growth rate of stainless steel, to determine the influence of thickness, and in the end to determine the influence on geometry, because we also are working on IPE beams, and we want to see like how the cross section will influence the crack growth rate, and if it will have any influence at all. So I thank you for your attention. I'm open to answer any questions, and I also want to acknowledge financial support of the Brno University of Technology and Czech Science Foundation.